Okay, question 3 is a composite question and it's a bending problem. So what we're going to do to tackle it is we're going to basically model this composite as if it was one solid material. So you've got to choose your base material. Usually I think you would choose the base material to be the material that has the lower Young's modulus, which happens to be the material that we have the dimensions for this section A, where the aluminium is. If it was the other way around, I possibly would still use the A as my base. Anyhow, decide which material you're going to use to model the whole thing. In this particular case, we're applying a force. We're going to create a bending, and we're interested in the bending stress that creates. So what I can do then is to take my B. Notice that my B is made out of brass. My brass has got Young's modulus of 101. So I need this to create my diagram. So my brass is got a higher Young's modulus, which means it's stiffer. Okay. So we will say that we've got our section A, which we're saying stays the same. And our section B, what I'm going to do is replace that with aluminium, which has a lower Young's modulus. So in order for this section B to get the same stiffness as the brass section, I'm going to have to extend it out. So it then becomes in effect like a T-beam. Okay, does that make sense? So this has the same Young's modulus as this now, but because we've made it wider, that will make it a little bit more stiffer to try and bend. So we're going to try and make it the same sort of stiffness now as, or have the same sort of forces going for it as if it was a piece of brass, which wasn't so wide. That's the concept. So on my diagram, I am going to use this N factor term, which is going to relate to the Young's modulus of brass against the Young's modulus of aluminium. So that's 101 divided by 68.9, and that's a ratio of 1.465. 9, I guess. I want 5 sig fig or thereabouts. So from here to here, we know it has depth of 50 millimeters, and from here to here, it's got a depth of h. The width is 150 millimeters. The width of the top section, well, to work that out, I'm going to use the fact that I know that this ratio times it by this scaling stiffness, is therefore going to give me in effect this width here. 219.885. Okay, so the first part of this question is determine the h. And what else do we know? So we've got determine the h, so the neutral axis of the beam is located at the seam. So we know that the neutral axis is here. Well, this is an unusual question because normally you're asked to find the neutral axis. So in this case we've got neutral axis equals the sum of areas times by their centroid locations divided by the areas. So my bottom, so if this is where my neutral axis is going to be, I know the centroid or the YC to get from there to there is going to be actually no, I'm going to do it from the bottom, aren't I? So this will define this to be my y equals 0. The distance to get from here to here is going to be half of the 50. So you've got 150 width times by depth of 50 times by the centroid, which will be 25, which is the 50 divided by 2. Okay. Now for the top section, we know its width is supposed to be 219.885. We don't know what its height is, so that's the area. And as far as where's its centroid, well, that's going to be based upon h plus 50, rather half h plus 50 I should say. So half that h plus this distance from here to here, and then you're going to get the centroid location. Now let's divide this all by their areas. So we've got 150 times 50 plus what, 219 times h, and we got what something is looking a bit of a mess. We know our y neutral axis is supposed to become at the seam, so it's supposed to be at 50. So that's supposed to equal 50. Fortunately, when we multiply this out, we end up with, I'm not going to do the sums, 150 times 50 times 25 plus 219.885 h half h plus 50 equals, so we've then got 150 times 50 times 50 plus, now let's try and rearrange it so it looks more obvious, 219.885 And so I'm multiplying this term here. Then I want H. And then I want 50. So the thing that makes this question actually doable is the fact you might notice that this times this equals this term here. So you've ended up actually with an expression which has just got h squared in it. So rearrange that and you'll find that you only end up with h squared. Okay. I didn't actually do the sum there, I just did everything on my calculator, and I then got h to be 41.297. Which, okay, so that matches up with potentially A or B. So we're still not done. The next thing we need to do is start looking at the bending equation. So let's take the engineer's bending equation. So M over I, we don't need the last bit, is stress over distance away from neutral axis. So what is the maximum moment the beam will support? So we're looking for the M. Therefore M equals stress times the I divided by Y. So unfortunately we're not finished. We've got to find I. So I is going to be the sum of 1/12 BD to the power 3's plus A H squareds. So I worked them out. You should be able to do that yourself. So we work out that to be 2.8525 times 10 to the 6, 10 to the minus 6. That's my 12 BD to the power 3's, and then my AH squareds is 8.55 9 times 10 to the minus 6. So I get a neutral axis, a second moment of area for the girder to be 1.14, 12 times 10 to the minus 5 meters to the power 4. So, what next? The next thing is to work out what your what your bending moment is going to be in potentially either of these two sections. And it's saying, what is the maximum moment this beam will support for the aluminium, where the maximum allowable stress for the aluminium is 128 megapascals, and for the brass 35 megapascals. Let's do the brass first. You can see why I'm going to choose the brass first. No. So let's do the aluminium first. We want to do the bottom section first. That's not because I'm assuming the bottom section is going to have the value. There's too much going on to be able to guess which one it's going to be the correct result. So for the bottom section, for the aluminium, you want to take your I value, so you've got the 1.14 times 10 to the minus 5. Then you want to take the stress, so we're taking that from the question, so that's the 128 times 10 to the 6. And then you want to take the distance from the neutral axis to the most extreme point, which is going to be 50 times 10 to the minus 3. So that gives me a result of 2.92 times 10 to the minus 5. Well, actually, that becomes to the minus 1, I think. Right, I've made a mistake with units. Let's check my units. So 1.14 minus 5 times 128 to the 6 divided by 50 to the minus 3. Okay, so we've got 29. Which kind of seems wrong. So you got 29 kilonewton meters. Seems wrong at first, but when you think about it, this is the maximum bending stress you're allowed. So you've got 29, which is way above all these potential answers we've got here. So basically what this is saying is the aluminium's fine. You can go up to 29. So there must be a lower value that we're looking for. So although you're saying maximum moment, that actually means you're looking for the lowest moment value, and it's not going to be in the aluminium section. So now let's look at the brass section then. So let's imagine we're doing the same thing, and we're going back to our diagram here. So we're putting the I value. We're putting its maximum allowable stress. So that's much lower, 35. And the extreme distance from here to here will be the H value we calculated, which was the 41. 0.3 times 10 to the minus 3. So let's put that in a calculator and see what we get. So you get 1.14 to the minus 5 times 35 to the 6 divided by 41.3 to the minus 3. Press my enter button, and I'm going to get 9.66 times kilonewton meters. So this value, notice it doesn't equal either of my values here. So what's going on? Have I made a mistake? The final thing you've got to consider is that this is the maximum bending moment, and we're using this model here to find out what the stress is. But we're not actually in a bit of, what would this be? A bit of aluminium that's been stretched out. We've now got to imagine that we're going to convert this model back to this model here. So if I start slowly replacing this stretched out bit of aluminium and start squashing it back, by doing this, changing it magically, like one of those photographs, changing it magically back into what is it? It's going to be brass. That will have the effect of changing the stress, which will be based upon this N factor. So we're changing the material type. So you actually want to take this value and now divide it by the N, so that it's actually going to be the stress what you would expect for the material when it's in brass to be experiencing. So you need to divide your answer by 1.4659. And now we are again getting a value which looks like one of our possible options. Got a bit of truncation error here, but we've got a result now. So we've now got this one here. So you can see that we're going to go for answer B. Okay, so the bending stress will actually be less than, because this is not the correct model. We have to go back to this model, and the stress that was being experienced, if we imagine this whole thing to be aluminium, is going to be higher than the stress than if this was actually brass. Another way to consider it would be is that you're changing the cross-section area, you're scaling the area by the width. So you're scaling it back down by this almost about 1.5 ratio.